Good afternoon. Today I'll be presenting my report for Math 1318, Time Series Analysis, Final Project Presentation. The topic I have chosen will be a forecasting of monthly mean sunspot numbers. The dataset that forms the foundation of my analysis comes from the Royal Observatory of Belgium, specifically from the Solar Influences Data Analysis Centre, also known as the SIDC. The dataset covers the period from January 1749 to January 2021. Giving us around 272 years of data on monthly mean total sunspot numbers. This equates to around 3,000 observations. For the purpose of this analysis, and due to computational limitations, I've subsetted the initial dataset to only include the last 30 years of observations, leaving me with around 300 rows of data. A little overview of sunspots are that they appear as temporary darker spots on the sun's photosphere because they are cooler than the surrounding areas. These are significant as they are associated with solar flare phenomena that can profoundly impact Earth's atmosphere and climate. First, looking at the time series plot, it is evident there's a cyclic trend or pattern occurring every 11 or so years. This fits in with prior literature regarding solar cycle patterns. These patterns help one to understand the variability of the number of sunspots found during these 11-year solar cycles. This observation also highlights the presence of strong seasonality in the data, with the variability and declining trend also suggesting that the data may be non-stationary. Looking at the seasonal decomposition of the time series displayed in the second plot, we see three more distinct components. Firstly, the trend component, which shows a long-term movement of sunspot counts. The seasonal component, which confirms our previous idea of strong seasonality, evident by its consistent nature. And the residuals, which after accounting for the trend in seasonality, show some variability but no systematic pattern. From this initial analysis, it appears that an ARIMA or SARIMA model would be suitable due to the strong seasonal pattern and the apparent trend. However, the presence of non-stationarity means that the series may first need to be stabilized via differencing. The series first underwent first-order differencing, and after confirming by an ADF test, the series was now stationary. The seasonal components were then identified via the use of ACF and PACF plots on the difference series. The ACF's initial significant spike suggested a moving average component of 1. The PACF followed suit with justifying an autoregressive term of 1 as well. This led me to explore 6 ARIMA and SARIMA configurations, which are noted on the slide below. For the SARIMA models, however, the seasonal period was set to 12 to reflect a midpoint between solar cycles as well as seasonal annual cycles. Looking at our ARIMA models, starting with ARIMA 110, we got an AIC value of 2,871. However, significant residual autocorrelation indicated that this one may have not captured all dynamics effectively. Our second model, ARIMA 011, had a better AIC at 2,844. However, it still had noticeable residual autocorrelation. Finally, our ARIMA model of 111 was probably our best ARIMA model with the lowest AIC of 2,837. And it also had minimal residual autocorrelation, suggesting out of the three, it had the best fit. Looking at the SARIMA models, starting with 110, it had a higher AIC at 2,931. Our second SARIMA model, 011, had an improved AIC at 2,783, as well as a better handling of the residuals compared to the previous model. Finally, SARIMA 111 stood out with the lowest AIC of 2,778, as well as having optimal residual metrics. Thus, it demonstrated the best fit amongst our tested SARIMA models. From these, the ARIMA 111 and the SARIMA 111 models were chosen to be investigated further. In this step, the chosen ARIMA and SARIMA models had a residual analysis taken to see if they adequately capture the underlying patterns without leaving significant autocorrelation or systematic trends. Looking at our first ARIMA model, we can see it displays quite random residuals, and the ACF and PACF plots help to confirm minimal autocorrelation, pointing to a potential good fit. Next, our SARIMA model also offers random residuals with no significant autocorrelation present. Thus, both these models will be undertaken to continue for the forecasting. Looking at the forecasting of the next 10 series points for the models, we can see for the first ARIMA model that the sunspot number forecast stabilized at around 14.5 per month. The model forecast can be seen as quite conservative, with narrow confidence intervals indicating less variability in the predicted values. On the other hand, for the SARIMA model, we can see the forecast start at around 6 sunspots indicated in February and increase to around 16 by November. The confidence intervals for this model are noticeably wider, particularly in the 95% confidence interval range, reflecting greater uncertainty in its predictions. In summary, both models provide forecasts with distinct characteristics. The REMA model suggests a period of low and stable sunspot activity, while the SARIMA model indicates potential for higher variability.